Hello, I'm Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. This video is tied to the course Intermediate Thermodynamics, and in this lesson we'll be looking at the basic conservation equation. Our goal here is that by the end of the lesson, you should be reminded of the basic form of all conservation equations and be able to apply it specifically to conservation of mass. We need to start with discussing a control volume. We can do either control volume or a control mass, but the concept is essentially the same. We're going to, for a control volume, carve out a specific volume in space, and we need to define the boundaries. For this volume, this space, for any conserved property X, some of the material X is or material, energy, momentum. Some X is in the volume initially. Some X will enter the volume. Some X will leave the volume. Some X will be in the volume after a period of time, and some X might be generated or converted into something else. When we write this as an equation, we get the general form of the conservation equation. So for X, the amount that is in the system at time t plus delta t minus the amount that was in there at the initial time t is going to be an accumulation in the system over time delta t. This is going to equal the amount of X that moves in and out of the system. So the amount of X that crosses into the system between our initial and final time minus the amount that leaves the system between the initial and final time. This plus the amount that is generated, or the negative of this is being destroyed, within the system between the initial and final time. This combination is our conservation equation. We can apply this to total mass. We can also apply this same equation to the mass or moles of a particular component, or we can do it for momentum or energy. There are two favorite special cases that we like, and one of these is the steady state equation. For steady state, you don't have any change over time, and so we're not going to be in these cases having the anything changing within the system over time, because the snapshot at time 1, time 2, time 3 will all be exactly the same. We may have material flowing in, but it's a steady amount at all times. And we may have material similarly that flows out. But if we have no change over time, we cannot have this generation within the system over this time period. It would have to be at a steady rate. For a closed system, we're going to basically have nothing flowing in or out, but we can have changes within time. We're going to be applying these for mass, fairly easy to keep track of, and then we will also be doing this with energy. We'll be looking at mass of just components in the system as we move into reactions. So this little quick video has given us sort of a foundation for going on to study the first law of thermodynamics and many of our other courses that we do as engineers. Thank you for listening.